when suddenly a car slams into the side of your vehicle. The windows shatter and glass is spilled everywhere, hitting you in the arm. What results is a huge gash with blood spilling everywhere. You scream in pain and call out for help. Problem is, no one is around to hear you. Suddenly, a bright idea flashes into your mind. Why don't I use my coagi coli that is conveniently sitting in my glove box? It has the ability to clot blood quickly and efficiently. And this brings us to the topic of our presentation today.
Hello, we are members of the Lethbridge High School iGEM team, and this year our project called Coagi Coli is focusing on encouraging faster blood clotting at the wound site to decrease the amount of time it takes to form a clot, as well as decreasing the amount of time or blood that you're going to be losing. We will be doing this by introducing our own coagulants into the bloodstream to successfully bypass several steps in the natural clotting pathway.
So, did you guys know that over 500,000 people bleed to death each year, resulting from extreme trauma forms such as traffic accidents or combat wounds? Or that approximately 40% of trauma-related deaths are due to the results of extensive bleeding or the effects of a hemorrhage? We realize that this is a worldwide problem that needs our attention, and we want to decrease the amount of deaths that are being caused by extensive bleeding. So how exactly are we going to do that? Well, we're using components of snake venom, which has the ability to skip several steps in the natural blood clotting cascade, therefore decreasing the amount of time it takes to form a clot, thus saving the patient's life. This project will impact the lives of many people, ranging from military personnel to law enforcers, and even to myself and all of you. What is important to know before we move on to the rest of our presentation is that this is a unique project that has never been attempted before by any other iGEM team to the best of our knowledge. Therefore, we hope that the knowledge gained doing this project will be used by teams in the years to come. But before we move on to the rest of our presentation, it is important to address the science behind it. Blood coagulation is an important process that the body undertakes to prevent excessive bleeding and hemorrhage. Platelets and proteins present in the blood stop the bleeding by working together to form a clot over the wound. In order to do this, platelets converge at the site of the injury and attract other platelets and cells to form a plug and seal the wound. And while this happens, the natural blood clotting cascade takes place. This is a natural occurring process that is highly regulated and follows a specific order to obtain a fibrin mesh at the wound site. Basically, there are two pathways known as the intrinsic and extrinsic pathway, and both of these pathways eventually lead to the formation of prothrombin activator factor 10. Once this is activated in the presence of certain ions, it leads to the conversion of prothrombin into thrombin. Now, once a good amount of thrombin has formed in the blood, it leads to the conversion of fibrinogen to fibrin. Factor 13 then acts on the fibrin to stabilize it. And finally, we have come to a successful clot as platelets and cells attract each other and stick together to form a stable clot at the wound site.
So with the knowledge of how a clot forms fresh in your mind, here's a list of products that are currently available on the market. However, these products are often expensive, like to seal, slow, like quick clot, or do not interfere with the natural blood clotting cascade, like Duracell. Zinta is for people who are only deficient in factor 13, and Our project, however, uses components of snake venom to activate the natural blood clotting pathway. The snake venom we chose to use was from the desert horned viper, also known as the Cerastus cerastus snake. We chose this venom because it's small enough for us to use from E. coli and it's not very complex. We chose this venom because we chose not to use the whole venom because it could pose possible health risks to humans.
An important aspect of our project this year was the interviews that were conducted by members of our team. We had the chance to interview Dr. Ed Pritzio from Canadian Blood Services, Dr. Bruce Ritchie from the Department of Hematology at the University of Alberta, and an expert from St. John's Ambulance. Each interview provided vital feedback that directly affected our course of thinking for the design of our product. For instance, St. John's Ambulance commented on the different application methods that we could use, such as a gel or bandage, And after our team discussed the pros and cons involved with each method, we came up with the final application method we have now, with the help from this interview. And then Dr. Bruce Ritchie also suggested a way we could use for an application process, and he gave us the idea of using a pre-filled syringe containing our construct as a way to apply it to the wound. And finally, Dr. Pritzio from Canadian Blood Services commented on the design of our product. For instance, he advised us that using a whole fibrinogen molecule would result in problems when used in combination with the snake venom because of the size difference between the two. He also suggested ways that we could improve the safety of our construct by engineering our protein's serasticin to be able to switch off, as well as using a solid matrix to prevent the diffusion of venom from going outside of the wound. For our product application, we will be using a pre-filled syringe, which will be followed by a bandage for sealing it in place. We took the advice from the interviews, and we conducted research on our own, and basically, we discussed other application methods such as a spray gel or gauze, but we chose Dr. Ritchie's advice for the pre-filled syringe, and we found out that other blood coagulants used a syringe such as Pfizer and Syntha. And for the bandage, we found that it was the most resistant in cold temperatures, it was the easiest to apply, and it was the most popular answer on our survey that we conducted. For our first construct, the purpose is to produce a sufficient amount of enzymatically active venom while also being able to control its localization. In order to do this, we will be using a medium to strong RBS promoter, which will produce our venom at a slow enough rate to allow our thioisomerase to catch it in time. We then have a periplasmic signal attached to both the venom and thioisomerase, and then there's serastinin, our venom serine protease, which we chose for its small size and unregulated ability to act on the thrombin. The benefits to using these in our construct is that it works until we can tell it to stop. It's easier to express inside of bacteria rather than expressing thrombin. It's easy to store and keep alive because of the multiple disulfide bonds it contains, and it skips the majority of clotting factors. But to make sure the venom stays localized and it's not traveling throughout the body, we're using a fibrin tag, which ensures that it gets polymerized at the wound site. And then there's our thioisomerase, which is important for helping the venom fold by bridging multiple disulfide bonds. And then we are sending it to the periplasmic space because it's more oxygenated, which will be a better situation for our venom folding. And there's how our fibrin will be localizing the venom. For our second construct, we haven't done any lab work on it yet, but the design of it is basically to complement the first construct, and it will be applied by the bandage component of our product. And to do this, we will be using human factor 13A, which will finalize the process by stabilizing the clot, by constructing crosslinks in the venom fibrin mesh. And then we've deployed antimicrobial peptide LL37, which punctures holes in the outer membranes of cells. And what this does is it lyses our first construct since we sent it to the periplasmic space, as well as preventing contamination in the wound by basically exposing its contents to the environment, which effectively kills it.
What happened?
So this is how our construct works together. Venom, which is a thrombin-like, our venom is a thrombin-like enzyme, and that acts on the thrombin. So we put a thrombin cleavage site between human factor 13A and antimicrobial peptide LL37. And when they're introduced together simultaneously, it will cut and antimicrobial peptide will be allowed to function.
So yes, we are high school students working in a lab with pig's blood. So you may be wondering, how do we even get the pig's blood? Well, we get it from a local butcher shop in Lethbridge, which is called the Mad Butcher, and they donate it to us so that we can use it in our lab space. So pig's blood is a food product, and that's what we are using it as, but we are taking safety precautions and treating it as a potential contaminant to our lab space. So this is our first experiment that we did with the blood, and before we even put the blood into the petri dishes, we had it mixed in with heparin so that it prevents coagulation before we actually do want it to coagulate. So what we did is we added 10 milliliters of the blood into 5 standard petri dishes, and we kept 2 of these as our negative controls because we wanted to see how the blood naturally coagulated, seeing how we never worked with blood before. So then we added 1.0 milliliters, 1.5 milliliters, and 2.0 milliliters of our Viper cell construct to the 3rd, 4th, and 5th petri dishes, and we timed these dishes over the time span of 24 hours to see how they would clot. And as you can see by the dark red areas in our results photos, those are the areas that have resulted in coagulation. So the ones that had the 1.5 milliliters and the 2.0 milliliters of our Viper construct did result in the most clotting, and our controls resulted in very little to minimum clotting. So moving on to our second experiment that we did with blood, we had heparin mixed in again to prevent the coagulation, and then we added 10 milliliters of blood into petri dishes, and we kept 2 of these as just the regular blood with no cells added to them at all because we wanted to see how it worked. And then we had 3 dishes that contained our Viper construct cells, and then 3 dishes that contained a control protein cell. So then what we also did is we added an extra milligram of heparin to one of our dishes that contained our control protein, one of them that contained our Viper construct, and one of them that contained just the regular blood, because we wanted to see if the addition of heparin had any effect on the amount of time that it caused to form a half clot. And what I mean by a half clot is that we did eye observations when around half of the blood in the petri dish clotted. So these were